The next video is a really important video. It shows the process of how the different fractions of crude oil are obtained by breaking down that crude oil using two types of methodologies, if you like. There is what we call thermal cracking, and there is what is called catalytic cracking. Cracking, as I'm sure you're aware of, is to break up. So that's exactly what we're doing. We shall be breaking up the long chains of hydrocarbons in crude oil into smaller, more useful chains. Now that can be done either under conditions of high temperature and high pressure. That's what we call thermal cracking. So thermal cracking is the breakdown of hydrocarbons that are found in crude oil under high temperature and high pressure. It's over here in your slide. The alternative and the major type of cracking process applied in industry today is catalytic cracking. This is performed at lower temperature and it involves the use of a catalyst. From your year 9 chemistry, you should already be aware of the meaning of what a catalyst can do. A catalyst will speed up a chemical reaction under conditions that normally would not promote that reaction. The first example that comes to mind is, of course, the laboratory production of oxygen gas if you use hydrogen peroxide in the presence of manganese dioxide. Such production of gas, of course, cannot take place at the same rate in the absence of the catalyst. So, in the next video, which is your third video in this sequence of videos, you will find out how the cracking process, will lead to the different fractions of crude oil that you've already learned about in the previous video, in video 2. You will also be able to explain from the video that you are about to watch that short chain hydrocarbon molecules, as you can see in the first bullet, so short chain hydrocarbon molecules are the easiest to ignite. They are the easiest, if you like, to burn. And therefore, since they are easy to burn, they are more useful as fuels. A fuel is only a fuel if you can ignite it. That's why petrol, which is so easy to ignite, is used as a fuel in the internal combustion engine. Of course, as the hydrocarbon chain length increases, it becomes increasingly difficult to ignite the fuel. And the function of the longest chain hydrocarbons is definitely not as fuels. They can only be used as fuels if they are broken down into smaller molecules. So let's take, for example, a long hydrocarbon chain. So a long hydrocarbon chain as found in, for example, lubricating oil. It is one of the residual fractions that you get in fractional distillation. Now, as it stands, as it is, it can only be used to lubricate machine parts. But if that fraction were to be used for the purposes of cracking, for the purposes of producing shorter chain hydrocarbon molecules, then it could also be used indirectly as a fuel source. The fuels are the shorter chain hydrocarbons that would be obtained by breaking down that long chain hydrocarbon molecule into smaller molecules. You will also, now I strongly suggest that you replay the next video several times. It's the last bullet that you see in this slide. You will be able to write balanced symbol equations that describe chemical cracking. Now, as we said, chemical cracking is the breakdown of a long chain hydrocarbon molecule into shorter molecules, into shorter chain molecules. Balanced is extremely important. As you will see in the video, the commentator emphasizes that whatever the chain length of the starting molecule, the starting number of carbon and hydrogen atoms has to be exactly the same after the reaction has taken place. So now I strongly recommend that you move on to see the video, and as you've done with the previous videos, you return to this slide, check off your learning outcomes as listed in this slide, and return to reviewing the video. Once again, take note that at the bottom of this slide there are also the MEDSEC assessment criteria that you will keep building on by means of viewing these videos. Let's now move on to the next slide.
In this video, you will learn about the process of cracking, how it is carried out, and why it is done. From our video on fractional distillation, you should know that crude oil is a mixture of hydrocarbons with different carbon chain lengths. Smaller hydrocarbons have a lower boiling point and are more volatile, making them easy to ignite and more useful as fuels. Larger hydrocarbons have a higher boiling point, are harder to ignite, therefore not as useful as fuels. We use a lot of fuels in our day-to-day lives, driving cars, aeroplanes, lorries, and even heating our homes. This means there is a very high demand for small chain hydrocarbons. However, after fractional distillation, we find that we have a large supply of long chain molecules. The process of cracking breaks down long chain alkanes into a smaller alkane and alkene molecule. This allows the supply of short chain hydrocarbons to meet the demand for them, as the longer chain alkanes are broken down into shorter alkanes and an alkene. The alkenes are also useful as these can be used in the manufacture of plastics. Here is an equation showing that C12H26 is broken down into octane and butene. There isn't a set way that these molecules are broken down. In fact, C12H26 could also be broken down into decane and ethene, or even butene, pentane and propene, as these equations show. The large hydrocarbon is broken down in quite a random way. Just note that in each equation, of course, since we had 12 carbon atoms and 26 hydrogens going into the reaction, the same must come out. The process of cracking is carried out in one of two ways, either by thermal cracking using high temperature and pressure, or by catalytic cracking at low temperatures and pressures but using a catalyst. In thermal cracking, the large hydrocarbons are heated to temperatures up to 750 degrees C and a high pressure of 70 atmospheres. This high temperature and pressure breaks the bonds between carbon atoms to make smaller molecules. Catalytic cracking is the method used mostly in industry today. The large hydrocarbons are heated to around 500 degrees C and are passed over a zeolite catalyst. The catalysts chosen tend to break the bonds in the large hydrocarbons and make molecules of between 5 to 10 carbons in chain lengths, making them very useful in petrol. Now, at the end of this video tutorial, you should know that cracking is the process in which large alkanes are turned into smaller alkanes and an alkene molecule, and that there are two types of cracking: thermal cracking using high temperature and pressure, and catalytic cracking, which is the method preferred in industry as it uses lower temperature and pressure and produces more molecules that are useful in petrol.
video on the next slide is an excellent demonstration on how cracking can be done on the school laboratory scale. It can actually be mimicked, it can actually be demonstrated using a boiling tube setup. Now, I would definitely go through the video as you should have done with the other videos at least twice, okay? Now, I've listed once again the most important learning outcomes from the video. So from the video, you should be able to identify these learning outcomes that I've listed over here. There are 5 of them that I've listed in sequence. So what I did was I went through the video and I jotted down these notes as I went along. So basically the video that you are about to watch is a replication on a small scale, if you like, of how hydrocarbons are broken down in industry. Okay, so I am referring to the first bullet, okay, which is over here, and I am talking about the small scale reproduction of industrial cracking of hydrocarbons. Please always be aware of the meaning of a hydrocarbon. You should know this inside out at this stage. It is a substance, a chemical substance consisting of just 2 types of atom, hydrogen and carbon, and the hydrogen and carbon atoms and the carbon and carbon atoms are all linked together by covalent bonds. You should also be able to identify from the video the apparatus, okay? So look carefully. Take note of what the demonstrator is using, okay, in terms of glassware, in terms of heating apparatus, okay, in terms of collection of gases, okay. The collection of gases over water is already a collection technique that you should have learned already in year 9. Okay, when learning how to collect gases such as carbon dioxide, oxygen, and hydrogen in the lab, you will be able to identify also the chemicals that are used to perform the experiment. So typically, the demonstrator would be using a fuel such as paraffin, okay, paraffin oil, and she would be soaking mineral wool with it, okay, a very small amount, just 2 centimeters cubed is what she actually mentions in the video. And she also will be using a catalyst. Now the catalyst can be pumice stone, okay, which is silica based, or you could easily use pieces of broken pots, okay, so you could actually have a small clay based pot, break it up into smaller pieces and use that as your catalyst, okay, due to the silica content. Now you should be able to list from the video. It's the 3rd bullet. Now this is a very important thing. I will mention this time and time again whenever there is reference to an experiment which is done in the lab, the safety precautions that are required, okay? You should not work at all in the lab unless you can be sure that you are working safely. So take note of the personal safety wear that the demonstrator is using, and also the heating technique that she is applying when heating the boiling tube during the process of gas collection. Notice that she emphasizes that heating should continue throughout, and that the flame should never be removed until the delivery tube has been removed from the water in order to prevent back suction of water into the boiling tube, and which could crack the boiling tube. You should then be able to understand how the demonstrator checks the product gases for the presence of short chain alkanes and alkenes. So you will see that she prepares a sequence of test tubes. The first two collection tubes are discarded. They are put away because basically they would just contain the displaced air that was contained in the boiling tube, in the reaction boiling tube. Now the third tube would contain some gas that would result from the breaking down of the paraffin oil that is being used to soak the mineral wool. Okay, so the mineral wool is being used as a substrate in order to soak up the paraffin oil. The paraffin oil, as you will see from the video, is being heated in the presence of the catalyst. The catalyst is the broken pieces of pot or the pumice stone. Okay, as you will note from the video, from what the demonstrator says, most of the time she is heating up the catalyst and just glancingly heating up the fuel. Okay, the fuel requires only little heat to vaporize. Okay, whereas it is the catalyst that needs to be maintained at a high temperature in order to enable it to help, if you like, the paraffin oil to be broken down into smaller hydrocarbons. So when you are checking for odor, the odor would be typically the same odor of camping gas or the same odor of the gas mixture that you have at home. Okay, so you are already familiar with what liquefied petroleum gas or domestic gas smells like, and you should be able to identify it from the third test tube as she explains. Now, the fourth test tube, okay, which would also contain this gaseous vapor that would result from the cracking of the paraffin oil, is checked to be a gaseous vapor by ignition. So the third test tube was checked for odor. The fourth test tube is ignited. So if the gas content catches fire, that's further proof that you have cracked the paraffin oil. The paraffin oil, I remind you, is a long chain hydrocarbon. That's why it is an oil. But the gases that you are testing for in your boiling tube are very, very short chain hydrocarbons, typically no more than 4 carbon atoms in length. There is also it could also be more than 4 carbon atoms. I correct myself, but not much above that. Okay, the fifth test tube that is tested for is using bromine water. Bromine water, as you will learn from your organic chemistry, can be used to check for the presence of unsaturated hydrocarbons. So typically you would use bromine water to check for the presence of a carbon to carbon double bond. So basically what you would expect is this: if you've got a carbon to carbon double bond, okay, in the presence of bromine water would be represented, if you like, by 2 bromine atoms which are connected together via a single bond. This bond would break down. The bromine would therefore lose its orange-brown color and each of the bromine atoms would then would attach to the short chain alkene, which no longer remains an alkene, because once the bromine atoms add on, then you have one of the bonds building up. The double bond is in turn broken down. So typically, if you start off with an alkene such as ethene, okay, so which is C double bond C, and as you should be aware of, there will be 4 hydrogen atoms, okay, attached to those 2 carbon atoms. Okay, so it does take me some time to draw this, but I'm using a mouse. I don't have a pen to do that. So the bromine atoms will actually add on to the carbon atoms once that bond is broken. So the bond, the double bond is broken, one of the bonds is broken, and the bromine atoms will attach to terminal carbon atoms. In this case, I can't really show this all that clearly with this carbon because I'm very limited by the screen space. But basically, you have a bromine atom attaching to carbon atom number 1, which I could put in over there. So that's carbon atom number 1, and I would have another bromine atom which is attaching itself to carbon atom number 2. So basically, when she tests for the contents of the 5th tube using bromine water, this is the chemical reaction that is taking place. It's the bromine being broken down, and it is being, if you like, integrated into the alkene molecule. So once the bromine water is broken down, it no longer has the orange-brown color. We say that the bromine water has become decolorized. Another decolorization test is the test using acidified permanganate. Permanganate, as you should very well know from everyday life, has a purple, a very strong, a very dark purple color. Take the slightest grain of permanganate, dissolve it in any quantity of water, and it's almost magical how the purple color just keeps coming out of every slightest bit of permanganate, every slightest residue that you will have lying around. Now, when you test the contents of a test tube containing an unsaturated hydrocarbon, so the 6th test tube would presumably also contain a short chain gaseous alkene. Let's say it's ethene. Okay, once again, ethene, as with bromine water, has a double bond. Now that double bond is available for reaction. Now with acidified permanganate, the acidified permanganate will break down that double bond, and in turn the permanganate will lose its color. It becomes decolorized, as the demonstrator will show. She says that the permanganate solution will either turn colorless, or you will have the appearance of a brown deposit at the sides and the bottom of the tube. Now the brown deposit, okay, is due to manganese in a different oxidation state than in permanganate. Okay, in permanganate you have a very high oxidation state. When it turns brown, it's a lower oxidation state. So that's what takes place when you add the permanganate to the gas that is contained in the 6th test tube. So both tests, both the bromine water test and the permanganate test, are tests for the presence of unsaturated hydrocarbons, which are short chain gaseous alkenes. Okay, very good. Now I advise you to do as you've done with the previous videos, of course. Go through the video, then get back to this slide where my commentary will be much more understandable once you've seen the video for the first time. I also strongly recommend that you see the video a second time. Take note also of the assessment criteria that the video and that this slide satisfy in terms of the MEDSEC syllabus. You can see the MEDSEC criteria at the bottom of this slide. Let's now move on to the next slide.
This experiment models the industrial catalytic cracking of long-chain alkanes and shows that some of the products have shorter chains than the starting material and that some are alkenes. They have carbon-carbon double bonds. The experiment is carried out in a boiling tube, and you need to start by putting some mineral wool, not cotton wool, into the bottom of the tube. The initial source of alkanes is liquid paraffin, which has about 20 carbons in its chain length. Use a dropping pipette to add liquid paraffin so that it soaks into the mineral wool. You'll need about 2 centimetre cubed. Just help that to soak in a bit. And just invert it to check if there's any excess, and if there is, remove it using a pipette. You don't want to get paraffin all the way down the inside of the tube if you can avoid it. You put that into the clamp and clamp it right near the mouth of the tube. Next, you're going to put some catalyst into the tube, and we're using pumice stone. But you can also use pieces of broken plant pot. Both of these are silica based, and they mimic the silica and alumina based catalysts that are used in industry. Now you want this tilted, but not so much so that all your catalyst falls to the bottom. This has got quite an open structure, which gives you a large surface area for the reaction to take place on. You attach a bung with a delivery tube to the mouth of your boiling tube. Have ready prepared a bowl of water with about 6 test tubes also filled with water and some bungs. Next, you need an assistant who could possibly be a competent student, although actually I often do this experiment with 2 students and don't get too involved myself at all. And what you're going to do is to heat using a roaring Bunsen flame, and the hottest part of the flame, which is just beyond the blue cone, and you're going to heat the pumice stone. As you do so, some gas will escape, and your assistant needs to collect the gas in a test tube. You want to get the pumice stone good and hot before you go any further. Once you've been heating for about 10 seconds, then you can flick across and just briefly heat your paraffin soaked in the mineral wool. Then go back and keep the catalyst hot. The whole time keep the catalyst hot and then just flick across to start the paraffin evaporating. You want to heat the pumice stone for about 10 seconds for every second that you're heating your paraffin. It is important to keep the boiling tube and its contents hot. If it is allowed to cool, water may be sucked back into the boiling tube and it can cause the boiling tube to crack. It's vital to watch the delivery tube for signs of suckback. If this seems to be starting, the solution is to continue to heat the boiling tube with the hottest part of the flame just beyond the blue cone, and to remove the whole thing from the water. It is tempting to push the Bunsen closer to the boiling tube or to remove the heat, both of which will increase suckback. And you can see there are some water drops coming up the tube, and if I just keep heating those, then they should come out. Continue until 6 test tubes of gas have been collected. Okay, when you come to the end and you need to remove it from the water and stop heating, it's really important that you remove from the water first and carry on heating for a moment. When you're happy that there's no water in the tube, you can stop heating, but I wouldn't turn off the Bunsen burner until you're convinced that everything has stopped. Then you need to test the gases. The first 2 you can discard because they will just be air from your boiling tube. Okay, the third one you can pass around the class, and they can have a gentle smell, and it should smell something like camping gas, which is a mixture of propane and butane. The fourth one you can attempt to ignite to prove that you have made a flammable gas. To the 5th tube, you can add a few drops of bromine water, which is just bromine dissolved in water. And shake it up, and you can see that the bromine goes colourless. This shows the presence of an alkene, or a carbon-carbon double bond. Similar reaction you can do with acidified potassium permanganate. A few drops into the test tube. Again, shake it up, and you can see that that's changed colour, and it will go either to a brown or a colourless solution, and again that shows the presence of an alkene or a carbon-to-carbon double bond.